Okay, last time we talked about the beginning part of our talk was on non-destructive evaluation, and I said that everything has flaws. To measure the flaws, energy must interact with the material. Virtually every portion of the electromagnetic and mechanical energy frequency spectrum has been used for non-destructive evaluation, or NDT is non-destructive testing. Really, I should have put NDT here. They use the spectra to do the test. The evaluation is more than just doing the test. It's evaluating the results of the test. So there actually is a difference in those two terms, but people often use them interchangeably. But nonetheless, there is a more precise definition, and I might as well do it. Non-destructive testing, which is a subset of non-destructive evaluation. You have to have some results in order to evaluate them, right? The smallest flaw size, which is readily detectable, is about 3 millimeters, and that's just what someone, well, let me back up. When you're doing these tests, usually you have a human interface that has to look and say, well, is that really something on the radiograph? I mean, that's what an MD does, medical doctor, when he looks at an X-ray. He has to determine if he sees something in all that mass of gray, right? And if you're used to doing it, you see things that a layperson is not going to be able to detect. But nonetheless, a lot of times it's just kind of shades, it literally is shades of gray on an X-ray, and you're trying to determine if there's really something there. If someone is doing this all day long, and for example, in a mill where they weld line pipe for transmission of gas or oil, large diameter pipe, there are people who sit there all day long, 8 hours a day, and basically look at a fluoroscope, an X-ray fluoroscope, of the weld. Now this is really exciting. I mean, this is literally watching, it's just as exciting as watching grass grow. And the thing is, there's a problem whether people are going to be able to, keep their attention up. But without too much difficulty, you can see something about 1/8 of an inch or 3 millimeters in size. Now, obviously, you can go down an order of magnitude if you do it with 10x magnification. And in fact, in a lot of cases, on aircraft or something, they may have an inspection that you have to do every couple of hundred hours because they know there's a potential fatigue crack starting at some rivet hole or something like that. And they'll tell you to go and inspect that area with a 10x magnifier. And obviously, you can get down to about a 10 mil crack, 3 human hairs in size if you're using a 10x magnifier. The problem is you have to know where to look. You can't expect someone to inspect a whole aircraft with a 10x magnifier. It would take forever. But, in fact, from either experience, because you've had cracks grow from one particular spot, and you know it is the high-stress location, or from analysis of a computer program or whatever, stress analysis, you know where to look. And so typically, you'll do that with 10x magnification if you're really trying to get things in a very, very critical, very small size. You have to do such things, for example, on things that get lots of fatigue cycles on them, like a propeller. Whether it's a ship propeller or whether it's an aircraft propeller, they go round and round. And if you know that they're failing, sometimes on aircraft they'll have I've seen inspections that have been required every 10 hours of flight. It doesn't get very practical to get much smaller than 10 hours of flight, because if you have to inspect the aircraft every hour of flight, well, obviously you don't even get to go where you want to go. You have to stop and inspect it in between. But I have seen things where they've discovered they had a problem they didn't know about before, and until they get a fix put in and a new part or a change of some sort, they basically will say you can't fly the aircraft unless you inspect it every 10 hours. And I mean, the military does that all the time. Not all the time, but I've certainly seen it occur many more times than once or twice. More typically, any aircraft, the Federal Aviation Administration requires an inspection every 100 hours of flight time. Now, if your car, you should change the oil about every 100 or 200 hours of driving time, because that works out to about 3,000 to 6,000 miles. Okay, kind of a typical average speed in your car between city and highway driving, unless it's all highway, but if it's kind of 50-50, is going to be about 30 miles an hour. So in 100 hours, you're going to get 3,000 miles. So you should change the oil. In general, automobiles we know enough about, we don't expect a catastrophic failure, which is the next point. The level of inspection and the safety factor that's used in the design or the proof testing or the design verification or whatever. There are lots of different safety factors, but the safety factor that's used depends on the level of inspection. If I do 100% inspection and I know there's not any flaws bigger than an eighth of an inch, or I have reasonable probability of knowing that, then I can tolerate a smaller safety factor. If I'm only going to do a random check, which means in a random check, I'm just trying to check to make sure the quality process is in control, there's a fair chance that in those other 90% of the uninspected parts that I've got something larger than that eighth of an inch flaw or whatever my limitation is on my defect size. So I need a bigger safety factor to allow for the lower level of inspection. So safety factor goes down as the level of inspection goes up. Of course, costs go up, so there's a trade-off here. Okay, designing something with a bigger safety factor adds weight and adds cost. Designing or requiring greater levels of inspection adds cost, so there's a clear trade-off there. If you're just doing visual, you may have a fairly high safety factor. For example, I mentioned, before I go into that, it's not only the level of inspection, but also the consequences of the failure. The way I used to talk, when I talk about Six Sigma quality, I used to say, if you're building Hubble's telescopes, this was a few years ago when we had the problem with the Hubble mirror. If you're building Hubble telescopes, Six Sigma may not be good enough, because the consequences of failure can cost you $500 million to fix it, or $1 billion to fix it. However, if you're making bricks for a building, 3 sigma may be good enough. I mean, what do you care if you get one defective brick out of 1,000, right? It doesn't really matter. Bricks aren't that valuable, and a single brick is not going to have a big consequence of failure if it cracked. However, a Hubble telescope, if you end up using the wrong geometry or whatever, and it costs you $1 billion to fix it, or if a lot of people are going to die or whatever, the consequences are such that you want to have a higher level of inspection. To give you an example, joists, the beams that go up to hold the roof or the floor of a building, they're redundant. So if one of them fails, usually the whole building doesn't come down. In fact, the whole building won't come down with a single one failing, if they're all marginal. The safety factor for joists I mentioned was 5/3. Now, the typical safety factor for the rest of the building, the main beams and columns of the building, is going to be a factor of 3 on design, actually 3.3. Actually, it's 10/3 if you want. It's a factor of 3.3 on the design safety factor, but since they're only going to do a visual inspection, according to the structural welding code, unless they call out something more critical, they need that factor 3.3 on the design. You only need the 1.5 safety factor in actual service, but if you're not going to do anything but visual, you could have big flaws there. And so you're going to put a bigger safety factor. So the design safety factor, if you look in the structural welding code, at the time of design is 3.3, but then the manufacturer is not going to be perfect, and so you lose part of that 330% safety factor, and when you're all done, if you got 150% safety factor, the bridge or the building probably won't come apart, okay? Because you expect to lose, if you're not going to do anything other than visual, you expect to lose some of your safety factor. If I take a ladder, which is another structural element, or a scaffolding, typically there's not redundancy there, and OSHA actually requires a 400% safety factor, not on the design, but on a proof load type of test, okay? Actually, it is on the design, but then they have to do a design verification test. They actually fabricate one, and in many cases, they actually load them up to 400% safety factor. Why? Because now you've got another element, and that's the human element. You may have a bricklayer who's told, don't stack all your bricks on the scaffolding that you're, laying bricks from, because bricks weigh a lot. Well, every now and then, some guy does, and they go up and they overload it by more than 400%. Well, typically, these things actually have a little bit more safety factor, and so they probably will hold 500 or 600% of the rated load. But sometimes they go above that. It's just incredible. They just think, oh, just keep piling things up, It's kind of like at a church supper once, someone said, oh, well, we'll just have everybody bring their electric skillets and we'll plug them all in and we'll fix this meal for a couple hundred people. I said, yeah, and where are you going to get the electrical outlets for that? Oh, well, there's plenty of outlets around the cultural hall. I said, yeah, but there's only a couple of circuit breakers, okay? You just can't overload things. So they decided to do something else rather than have stir fry or whatever they were going to do. Okay, any questions on that? So now, if we get into trying to understand what is a defect and what is a flaw, it turns out the non-destructive test folks have gotten fairly precise in their terminology. They don't call it a flaw, because depending on what you're doing, it's just this change of gray, or it's a little blip on an oscilloscope in ultrasonic. In X-rays, it's a change of gray on the X-ray. In ultrasonic, it's a blip on an oscilloscope. In penetrant inspection, it's a little bit of red coloring on a white background. So it's not really a flaw, it's just some what they call indication. Okay, you did a test, and the test came back and gave you an indication. An indication certainly doesn't mean it's a defect yet, even if it is a flaw, but an indication is not necessarily even a flaw. There may not be anything in the material, but this may have to do with some artifact of your measurement technique, rather than a true flaw in the material. Well, if you got an indication, that's your non-destructive test. Your non-destructive evaluation involves some interpretation. And if you say, oh, well, it's not relevant, okay, it's there, there actually is some flaw in the material, but it's too small to be harmful. Let's say it's less than 1/8 of an inch and you got a critical flaw size of several inches and the specification says you only reject things greater than 1/8 of an inch. Or maybe in some cases like undercut along the side of a weld, you're allowed 6% of the weld length over 1 foot or something like that by the code. Okay, so you can get 3/4 of an inch of undercut over a 12-inch length of the weld in certain applications. So if it's smaller than the specification, by the way, it does you no good to have a specification unless you have a criteria for acceptance or rejection. Okay, a lot of times people say, well, inspect it per such and such, and a standard code that's been around for a while will have objective criteria for acceptance and rejection. Sometimes when someone doesn't call out a code, but they call out some inspection technique without calling out a code, they'll say, well, use magnetic particle inspection. Okay, I can get an indication. Now how do I decide whether to accept it or reject it unless you give me a criteria? What size flaw is rejectable? Okay. So people sometimes forget, engineers sometimes forget to give a acceptance criterion. So anyway, if you have an acceptance criterion, you may determine it's non-relevant. You may determine that it was some artifact. It's not really a flaw at all in the material. It's some little scratch or something that showed up by your test technique, and it really is nothing internal to the material, and surface flaws are insignificant, or you had some noise in your oscilloscope or whatever. It's not real. Okay, your indication was a false indication. Now, the third possibility, it's relevant. Okay, well, if it is a relevant indication, it looks like it's big enough, you've got to now evaluate it. This is the non-destructive evaluation, and you either accept it or reject it based on your criterion. Okay. Actually, this little scratch might be over here. Anyway, there's that tree is not necessarily a perfect tree, but that's the general idea of the process you have to go through in non-destructive evaluation. Now, there's lots of different non-destructive test techniques. Ultrasonics, we're going to talk about. Radiography, we'll talk about. Eddy current we will also, actually, we'll talk about all of these. Eddy current uses an oscillating magnetic field to see if you have anything that will show up as a magnetic anomaly. The analog to eddy current for a non-conductive, non-electrically conductive material is dielectric. Okay, so if I've got a ceramic or a piece of plastic, which I can't use eddy current on because it doesn't conduct electricity, and therefore it doesn't have a magnetic signature, I can go in and I can basically do a capacitive measurement. In fact, that actually is a very good way for composite materials, these plastic composites, to see if you got delaminations. Okay, what was the aircraft, the American Airlines, and that crashed into Brooklyn or the Bronx or whatever, and it was a delamination that they had on the empennage, the tail fin, in production. It was an Airbus. So in Europe, they built this thing and they had repaired it. And I haven't been involved in that one, but they could have detected, or they may have detected by capacitive techniques, that they had a flaw, they repaired it, and in that case, they probably should have gone back and continued to repair it, because composites are very difficult to make a fully functional repair. Magnetic particle and liquid penetrant we'll go through, but basically this is something where you actually put a liquid on the surface. If you have cracks, the liquid will penetrate the cracks, and then you have different ways to try to see the liquid down in the cracks. Well, then coming down here, you don't have to worry about all this. This should be in one of your handouts, but it compares the capital costs, consumable costs, how long it takes, the effective geometry. Not all of these techniques work. If there were one non-destructive test technique that worked for everything, we would use it. Okay? We wouldn't be searching everywhere on the mechanical and electromagnetic spectrum for something that's better if we had the magic bullet that would always work. So there are all kinds of limitations. You could certainly make a full course or courses on just non-destructive evaluation rather than the 2 lectures that I'm going to give you. But to a certain extent, the part of the philosophy at a place like MIT and the old fire hydrant type of approach to education is to, as Professor Lagasse and I say, it's to sensitize you to what you need to know. Not that you were going to learn it, okay, in any great detail, but in fact to know that it exists, and these are some of the concerns, so that when you do need to know it, you can go and learn it. Okay, you don't have to learn it now. Okay, you only need to learn it when you actually get to it. For example, I studied Fermi surfaces and crystallography and all kinds of things as a student, and I've learned over my career that the way my career went, I didn't need to know those things, and so I've forgotten all that stuff, right? If I had to learn it, I probably could, but nowadays I just get a student to do it. So let's talk a little bit about radiography, and in fact, let's see what I have for radiography. Okay. Radiography consists of lots of things, but the first discovery of radiography was done by Röntgen, and this first radiographs from 1896, and it's a gunshot in someone's hand. Now, this is not the very first, I don't think this is the very first radiograph, but I think that Röntgen actually did x-ray his hand, but it's sort of a discovery, an accidental discovery. But here you can see the gunshot pellets, okay? I guess he got shot by a shotgun, and that's the shot, the lead shot in the hand. And that was one of the first x-rays, and everybody said, ooh, wow, this is really neat. We can do things with this. And they could, and they went off and they x-rayed people, and they thought radiation was sort of an interesting toy for a while as people learned to do things. They didn't realize it had really harmful effects. In fact, in the 1920s, after Madame Curie in France won a Nobel, actually she won 2 Nobel Prizes, but she won a Nobel Prize for some of the work she did on radioactive decay. People actually thought that radium was a health promoter. And there were people, you had to be rich to be able to do this because radium was an expensive thing, but they actually would drink radium in the 1910s and the 1920s or whenever, after Professor Curie had discovered this as an element. And they said it made them feel great. And all the way into the early 1930s, there's this one very wealthy man. Now, some people, basically radium, if you drink radium, your bones would start to decay. It decalcifies your bones, and you basically, people started breaking bones and stuff. But apparently, it made you feel good, you know, sort of like drugs. Made you feel good for a little while, whatever it was. But there was this one very wealthy man all the way into the 1930s who was sure that this was the health elixir for the centuries, and he had enough money, he kept on drinking it, and finally he died this terrible death as his bones just decayed to nothing. But anyway, we have since learned that you have to be careful with radiation, and I'll talk about some of that in a little bit. In fact, maybe I'll talk about it right now. No, I want to talk about types of radiation. We use X-rays. We actually do use gamma rays. I kind of misspoke yesterday when I was teasing about gamma rays from space. We do use gamma rays on Earth. We use neutrons. We use electrons in some cases, and sometimes people use positrons. So we use all kinds of radiation. We certainly use protons too. Basically, all kinds of particles and photon energy ranges to probe materials. And it turns out sometimes we do it just in a simple 2D projection, which is what we're most familiar with. Take a chest x-ray, you break a leg and they take an x-ray, or you go to the dentist and he x-rays your teeth. But in fact, people do tomography. Now, tomography is just three-dimensional x-rays. That's basically a CAT scan nowadays, right? If you go to the doctor and something's wrong, they can put you in a CAT scan machine, and basically it's just an x-ray machine that takes a bunch of shots from a bunch of angles. We have much better detection techniques, so the level of radiation that people use is much, much, much lower than it used to be. People are still afraid of radiation. Why are some people still afraid of it? Actually, when I was a child in the 50s, you go to the shoe store, they actually would radiograph the child's feet. They put the shoes on, and they had a little radiation, x-ray machine, and you stick your feet in there, and they would x-ray to see if the shoes fit right. And mothers thought this was wonderful. This was high technology, after World War II. They didn't realize that the dose they were giving the children was actually harmful, and so all of a sudden, kind of mid-50s, they stopped that, okay, when they realized that they were probably doing bad things. But that's, it took a few years as people learned more and more about things. And a lot of the stuff they learned about in terms of health effects was because of the atomic bomb and setting up the national laboratories. And they had, teams of very highly qualified research scientists looking at not just radiation and radioactive decay, but its effects on the human body. As they learned more and more about that, they came up with better and better detectors, such that nowadays, people worry about X-ray machines and things like that. And, at the airport, you shouldn't put your arm in. You can put your arm in there all you want, because you're going to get about 10 times as much radiation by flying from here to Denver, by being up higher and having less of the Earth's atmosphere to protect you from cosmic radiation, as the radiation you would get by sticking your arm in that machine. Okay? The machines now, literally, a flight to Denver gives you about 10 times the radiation, whole body radiation, that you would get by going to the doctor and getting an X-ray taken. I had to go to the dentist. I cracked a filling a couple of months ago, and I go to the dentist in August, and they just, laid about 40 pounds of lead, jacketing around me. I told the technician, this is stupid, we have to do this to protect you. Yeah, well, I took three flights this week. I got, big deal. What are you protecting me from, right? But it's because the public doesn't understand. So anyway, there are three-dimensional radiography, and people think CAT scans are wonderful. They don't realize they're getting about 1,000 X-rays in a CAT scan, as opposed to the old single X-ray. But don't tell anybody that, because they'll get all upset, right? They'll think they're getting an excessive dose. Well, it's like several trips that year to Denver, right, to get a CAT scan. But the CAT scan is basically just taking projections from a lot of different angles and letting the computer do tomography to go backwards. In fact, we do that with metal parts in critical applications, like valves for nuclear reactors or something. They may do full tomography, industrial X-ray. Now, it's a little bit harder because It takes more energy to go through a foot of steel than it does to go through 12 inches of the human body. And so it takes longer and it's more expensive, but we do tomography. Radioscopy. All these are a type of radiography. Radiography is just somehow making a projection, seeing through something, right, with either particles or photons. Radioscopy, instead of having film as the detector, you basically have a fluorescent screen. That's the old, the old movies where someone gets a fluoroscope image, chest X-ray. We don't do that as much because that took a lot more energy than the other types of detectors to make the phosphors work. But nonetheless, it's still used when you don't want to do film. However, now that things are digitized and stuff, basically fluorescent screens are sort of gone in general. There's something called Xerography, Xerography, and that's collected, that's where the X-ray energy is collected on a selenium screen. If you think it sounds sort of like Xerox, there's a reason for that. Anybody know why? That Xerox started on selenium, the photo detector, the little drum that takes the light charge when you scan the document, and you put the charge on this little drum. Originally, that was a selenium drum. Now we don't use selenium anymore. We probably did 25, 30 years ago. Now we have polymer systems that work just fine and are cheaper. And selenium is also a somewhat toxic material, so keep it out of the environment. Radiometry is basically what we use more now, where you collect it on a detector, digitize it, and then interpret it by, you can display it on a screen, but it turns out doctors and others can still see more if you turn it into a film. Because if you turn it into a film, you can change the light in the background to change the contrast between the different levels of gray. And if you really want to, well, typically you can measure about 2 to 4% sensitivity. If you have a flaw that's, let's say, 4% of the thickness of the material that you're projecting through, you should, with your eyes, a trained person should be able to see that difference in grayscale if you have everything set up properly. There are fancy machines that go through and do it electronically and go basically scan the image of the film and get greater sensitivity than the human eye usually can detect reliably, but that's not used that often. Now, any questions on those types of things on X-rays? You can take whole courses, and there are whole books written on how to do proper X-rays. Basically, for industrial X-rays, if you're going to X-ray a weld, and I don't know if I mentioned it earlier, basically within the last 10 years, for example, the U.S. Navy about 8 or 10 years ago, after doing studies in the early 90s, basically said no more X-rays in the ship. It's preferred not to do X-rays in the shipyard. You can now do ultrasonics. Ultrasonics has progressed to the point where you can detect any flaw with ultrasonics that you can detect with X-rays. Now, it turns out most of the commercial shipyards have switched because the Naval Sea Systems Command now says that you don't have to do this. And more of the industrial fabrication places that are not necessarily Navy shipyards, but some fabrication facility, more and more people are specifying ultrasonics rather than X-rays because each sheet of film might cost you 20 bucks to have someone come in and take it, and the cost of the film to get that X-ray. Now, one of the advantages is you have a permanent record. You've got the film. But it's not really a big deal nowadays. You can store lots of data, so you can store those oscilloscope traces from the ultrasonics digitally. And they have systems for that today. So it's cheaper. You don't have to use all this film. It's cheaper to use ultrasonics. One of the reasons it's cheaper is you don't have to clear out the shipyard or wherever the place is. If you go into the big dig, one of the things they'll be doing down there at nighttime when there are fewer workers around, there's still some workers, is they'll be doing X-rays of some of the welds on the structures. or any building around here. Typically in the evening, when most of the laborers are off site, you go in there and you do your x-rays. Now, you have to clear out an area. It may be 50 yards away for everybody within 50 yards, otherwise they're going to get radiated. And now the x-ray radiation is intense enough, because you're going through several inches of steel, potentially, that people need to wear badges, and you can easily get, in just a few minutes time or less, all the dose that you need to get, or you should be getting for a whole year. You can collect in a few minutes. Actually, I used to hear the stories that in India, in nuclear reactors, they have requirements that people not get but a certain level of radiation. In the United States, what we'll do is we'll develop all kinds of robots and stuff, and so if you have a hot part of the reactor, you'll send a robot in there because the robots can tolerate the radiation, right? Well, in India, supposedly, to repair some parts of the reactors, they will basically line up about 20 or 30 people, and they'll train them on a practice thing, and the first person goes in and he turns the bolt, 1/2 a turn, and in 30 seconds he gets his yearly dose of radiation. And the next person goes in and he turns the bolt a little bit further, and they basically do the repair by just sending in waves of people, one at a time. It's cheaper than robots if you got low-cost labor, I guess. But there are limits on how much radiation you can get. Now, to go and do something on site with things, it depends on what radiation you're going to use. It's easier if you can do something in the shop. If you do something in the shop, they use all kinds of linear accelerators or high voltage guns. And these things will go from a couple 100,000 volts up to megavolt linear accelerators that will go through 10 inches of steel. And that will give you some very sharp images. In the field, we have to use radioisotopes. If I go up in energy, if you remember from your physics courses, as I go to higher and higher accelerating voltages, 30, 50 to 100 kV, the relative intensity of the radiation coming off increases dramatically as a function of wavelength. So you get shorter wavelengths, you get greater, the peak changes, and all these variables make it complex to figure out what the right radiation to use is. In the field, you can't take a linear accelerator with you. They're just not exactly portable. You also can't just plug one into any old 110 volt outlet. You need lots of power. So in the field, we actually do use radioisotopes to give off gamma rays. Cobalt-60 being one, has a half-life of 5.3 years, and it'll go through about 10 inches of steel. Iridium-192 is more commonly used because it'll go through 2.5 inches of steel, which is about all you usually need, but it has a half-life of 74 days. So sometimes it gets a little pricey to keep on replacing it, but if you have a big enough business. Now, how do you do it? You basically have a cart, typically lead-shielded chamber, and your radioisotope source is inside this, and it's on a cable. So you put the cable that where you want to expose your film, you put the tube down here, and basically the guy just gets 50 or 100 yards away, and he cranks the cable, and the thing goes out of the shielded, protected chamber over here. And I pointed out some of these things get to be very heavy in one of my classes. For a cobalt-60 source, basically this thing could weigh 1,000 pounds, the thing that holds the source, because you gotta have lots of lead shielding if it would penetrate that much steel. Typically for Iridium-192, you may have little sources, this little thing with 100 pounds or a couple 100 pounds, but still, but you just push it out there, expose the film, pull it back, and develop your film. That's a problem because you got to clear out the building or the bridge or the shipyard or whatever you're doing. Now, you have some problems with orientation. And so typically, if you really want to know things quite precisely, you'll end up looking at several different orientations. If your crack is oriented through the projection, you'll get a very high intensity. If it's a lamination, you may not pick it up at all. But if the stress is in that direction, that that is critical for that type of flat lamination, you better do an X-ray from that direction too. So it's orientation dependent. It doesn't tell you everything as far as that goes. Now, there's an example in your handouts of X-raying a razor blade and an apple. Actually, if you go back years ago, the reason people on Halloween hand out candy that's all wrapped up and sealed is because there were wackos out there 40 years ago who would hand out apples and they'd slip a razor blade in there so the kid would bite into, cut their mouth. And people would poison things. There were a lot of wackos out there. So mothers and fathers will sort through their children's Halloween candy to make sure that nothing is contaminated. Anyway, if you want to, this is the table that goes along with that razor blade and the apple. If you use 0.154 nanometer wavelength radiation, it turns out that you can't even get through the apple at that wavelength. Now, if I go down by a factor of 2, because this thing is going up exponentially in intensity and stuff, you'll get about half the intensity through the apple, and nothing will go through that razor blade. So that's what you want to use. If you go up to 80 kilovolt radiation, and you're just X-raying an apple, you'll go through the razor blade too. And so you won't see anything because you just overexpose it. So you have to pick the right type of radiation for what you're using. So I guess the best thing is, rather than pretending you know something about X-rays, hire a technician from Wentworth Institute or somewhere who's gone through a whole 2-semester course on how to take X-rays, because there are lots of subtleties in what goes on there. However, just in general, when you go to do a failure analysis, one of the first things you should do is consider whether you can learn anything by doing some non-destructive tests to begin with. Typically, X-rays are great. You got a failed component, something failed inside, and everybody's sitting there wondering, oh, why did it fail? Well, what does a doctor do? If you come in and you're complaining about something, why did your body fail? Well, he does an X-ray or whatever. He does some sort of test. That's, hopefully if he's working on you, it's non-destructive. But you do a non-destructive test on the part. And a lot of times people just forget to do it. Sometimes I've gone out and said, I quite often say, well, let's do an X-ray. Because then we don't have to get permission from everybody because we're doing something destructive. We just go out and do it. And sometimes you learn enough from the X-rays that you don't even need to do anything else. And there have been times I said, I don't want to do anything else. I can see everything I need to see on the failure on the X-ray. That's like 10% of the time you get that kind of very positive result. Sometimes you see nothing on the X-ray. In fact, I thought about bringing some X-rays up to show you of an aircraft failure where we know it's the part that failed, but we didn't see anything on the X-rays that really was very exciting. But to give you some idea of what to look for in X-rays, there are standard books. I've got about a half dozen of these. They're probably about 20 or more of these things from ASTM, and each one of them they'll sell you. This is one of the smaller ones. They'll sell you this for probably $300 or $500. The bigger ones they'll sell you for about $1,000 or $1,500 a piece. But it's reference radiographs. For this one, for inspection of aluminum magnesium castings, and there is an ASTM standard, E505. So they give you a copy of the standard. That's wonderful. That's worth a couple bucks. And then they actually have plates, radiographic plates, that I'll pass one around. This is for aluminum die castings. These are actually film. This is X-ray film. You can't see a thing unless you hold it up to the light. Yeah, you can see it. And you'll see the defects in the casting, and they have it for different thicknesses of aluminum. They have, this is the go, no go. A designer can call out ASTM E505, it shall be better than film number 3 or whatever on this set of reference radiographs. So this is your objective standard, and the guy kind of looks at it and says, good, bad, indifferent, okay? And so there are different levels. As you go across there, it'll have some good ones and some bad ones. As it gets from the very best to the very worst. One of the reasons you have that, and actually this one I use more than any of the others that I have, because aluminum castings will always have porosity. It's just inherent. I mean, if there's any moisture in the air, the aluminum will react with the moisture in the air to form aluminum oxide and hydrogen. And hydrogen and aluminum will dissolve in the liquid, but it comes out as it solidifies, and you will always get some hydrogen-based porosity. So sometimes people will, they'll see a fracture on aluminum surface and aluminum casting, and they'll put it in the scanning electron microscope and they'll find, oh, here's a pore. Well, the pore is about 2 human hairs in size, and if you go through the fracture mechanics, the critical flaw size is ½ an inch or something like that. And they'll say, this is the cause of the failure. I found a flaw. They say, I found a defect, okay? It's not a defect at all, it's a flaw, and they all have it. The best quality aluminum castings in the world have small amounts of porosity. And if that's a defect and makes it unfit for purpose, then we should never ever use an aluminum casting again, which means most of you shouldn't drive home. Because believe me, your engine blocks, many of them are aluminum, okay? It's absolutely absurd. The people who hang out with a shingle and say they know anything about failure analysis, there should be some sort of qualification program for people like that. I mean, we require MDs to at least do some sort of competency test, but I mean, there is no competency test for general purpose consultants, whether we're talking engineering or business consulting, which is even worse, okay? And you go, oh, I'm a consultant. That means you're out of work, right? In fact, that does mean you're out of work many times. They just say, I'm now in consulting, which brings up, you've heard the definition of a consultant as anyone more than 50 miles from home, right? But the best definition I know of a consultant is someone who borrows your watch, tells you what time it is, and then keeps it. Now, I heard that from a consultant, a guy who was the vice president of Bain now, but in any case. Okay, any questions on that? If not, let's go to ultrasonics. Ultrasonics are basically just sound waves going through the material. We call them ultrasonic because in a solid metal, we have velocities on the order of 3,000 meters per second. At those speeds, to get wavelengths that are going to give me a flaw size, right? Remember, velocity divided by wavelength is equal to frequency, right? If I put 3,000 meters per second in here, and I put a wavelength in here of 3 millimeters or something like that, a size flaw I want to detect, you will get very large frequencies, okay? Do it for yourself, but you're going to be in the megahertz regime to be able to detect the size flaws that you want to see by ultrasonics, and you can't hear in the megahertz regime. Now, one of the wonderful things for people who work in ultrasonics is there's lots of types of waves. There are transverse waves, which is like taking a material and hitting it and the stuff, and there's also longitudinal waves, okay? There are actually probably a dozen different types of waves. There are Rayleigh surface waves, there's Lamb waves, L-A-M-B, named after somebody, I think. All kinds of waves, and that means that people will be studying it for years and years to come. It's very, very complex to understand what's really going on, but in the simplest sense, you put a transducer on here. Now, this is a piezo-electric transducer. Typically, piezoelectric is just a material that if you put an electrical input in, you'll get a mechanical vibration out. Or if you put a mechanical vibration in, you'll get an electrical input out. So it turns out you can use the same transducer as both the output signal, the test signal, and the sensor to detect the wave coming back. Or you can do what they call pitch and catch, where you have one transducer that sends out the sound wave, and then you have another one over here that catches the sound wave. Okay, so pitch and catch. In any case, here's your transducer. It's going to vibrate things just like the piezoelectric. Well, if you have a electric stove or whatever, and you hit a piezo, you basically hit something to get it to start, and you hear click, 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 and it sends these little sparks. That's just a piezoelectric crystal that they hit a mechanical vibration and they get a high voltage spark out. So you send out something, and when it hits the other side of whatever it is, you will get a reflection wave back. You catch the wave. So the input pulse goes out. This is your oscilloscope trace. It hits this thing. They're actually showing a flaw over here. They call it the discontinuity echo. Okay, well, there is a discontinuity when you change from solid to air. But in this case, if you do all this, if there was nothing in the thing, it would go all the way to the back side and come back, and the time that takes, this is time on this axis, you'll get a peak over here. If there's a flaw in between, you'll see grass growing in the area in between. So here's your output signal, this is your reflection back for a good part, and this is something in between. Now, you can pick up things pretty well. It's gotten better and better. Actually, I guess I have another picture here showing pitch and catch. So here's the initial pulse, the echo off the rear wall. If you have a defect, it'll be somewhere in between. It takes shorter time to traverse that than to go all the way across. So on your time base, you'll see grass grow in the middle with a defect. Here's the pitch and catch, where you go down and sender and receiver. Okay. There are some cases. Let me just show you one. And if you want to go to, I didn't go check, but it would have been 3371 lectures last year, where I was doing some naval things, and then we had a flaw. You can hear the whole story. I've shown you some of the forging things. I want to show you a picture of the. Time here. We had a great big casting. It was the tail shaft of a ship. Here we go. And this is the end of the propeller shaft in Singapore. Great big forging, 33-inch diameter, has a thermal residual stress crack that was hidden inside, but inside of that crack grew from a casting defect from the ingot that was the size of a football. That's a pack of cigarettes sitting inside the defect. That's the initial defect from the steel mill. And the heat treating shop, they grew that little defect into something, went all the way across there. The final solid structure was the smooth stuff, which grew as a fatigue crack. So this whole story brings in residual stresses, thermal stresses, it brings in defects. Well, the one thing I wanted to point out, without telling you the whole story, is the ultrasonic inspector at the steel mill found the flaw. And he takes it into his boss, and he says, I got an indication. Well, it turns out, because they had been screwing up on this job, they had already scrapped a couple of parts. His boss threw him out of the office and said, forget it, I don't want to hear about it. So the guy wrote it up, and he has this nice little picture in his notes showing a football-shaped defect right in the middle that he found by ultrasonics, files it away. They ship the part to the shipyard, okay? It goes into service, okay? And it breaks out in the middle of the Philippine Sea when the thing was fully loaded with liquid natural gas, $7 million repair. And they found it. But the boss didn't want to hear about it because they were losing their shirt on this job. So shoot the messenger, right? And then you go back and you find it. You find the ultrasonic test report right there. And I remember being there when the guy told his story. Oh, yeah, I went and told the boss. Anyway, another little story about human nature. It's not technical problems, it's people problems, right? Thank you. See you tomorrow.